So my name's Chris Pickard. I was a professor at UCL and a colleague of Alex and a member of the TYC for many years, up to 2015, and then I moved to the Cambridge Department of Materials and Metallurgy, where I've continued my research. So I've been involved in a variety of things over my career. I'm one of the developers of the CASTEP DFT code, and I spend a lot of my time working out theoretical spectroscopy, so NMR or various core level spectroscopies, and also a lot of time building up the database of pseudopotentials, which probably you've heard a bit about pseudopotentials in this course. At least for the CASTEP code, I'm the one that's responsible both when they work and when they don't work. So we spent a lot of time designing the pseudopotential code and developing data sets of good parameters. But following on from that, now it's probably 15 years ago or so, I got interested in the field of structure prediction. And this was in the early days when multi-core computers were starting to become widely available. So when I started my PhD, the vast majority of the calculations you do, unless you're on a big supercomputer, were serial calculations, just a single processor available to one researcher. And typically you had to book your time in front of a workstation to go interact with it and so on. This was before the sort of cheap PC Linux boxes that took over the world afterwards. But there was a change in sort of the early 2000s where Intel-based or AMD-based chips were available for Linux servers, and it meant that pretty much anyone then could have access to a parallel computer. And there are different ways that parallel computers could be used, and probably for most of this course you've focused on if you're thinking about parallel computing, it's taking a very large calculation and breaking that single large calculation into small pieces and then enabling it to run when it wouldn't run otherwise by going to a bigger computer of many cores. But there is another approach, and that's where you do fairly small calculations, but you do many of those small calculations on each of the different cores. And I think probably you'll be quite familiar with this now, but in the in the early 2000s, this concept of high throughput computation was quite novel. There were two kind of strands to that. There was the strand that you may well have heard of, pioneered by Gerd Sieder in MIT, who developed the materials project. And I'm no doubt if you've been doing any research in this area, you Google a material and you'll probably get hits from the materials project now or something similar to get you started. That was built up in those days. But a parallel and different strand was structure prediction. And myself and others around the world, instead of doing high throughput calculations on known structures, we tried to use these computers to uncover new structures, new materials. And so this is structure prediction. So yes, so this afternoon we're going to break into two parts. Part one is going to be focusing on high throughput computation, and part two will focus on structure prediction. I'm not completely sure exactly how long each part will take, but my plan is when I get to the end of high throughput computation, we'll have a quick break, and maybe I'll at least walk around a little bit and then sit down again back in front of the screen to carry on. I'm extremely keen if any of you want to ask any questions and direct me this afternoon into areas that maybe you don't think I'm going to talk about. I'm very happy to do so. So I've got a bunch of slides, but I'm more than happy to discuss things that you were interested in. So probably I'll try and keep an eye. I've got your pictures to one side. So if you put your hands up with the little yellow hands or whatever, I'll watch out. I'll watch out for that. For some reason, I can't see any chat. So maybe if you chat, I won't see it. I don't know why I can't see any chat at the moment. So probably best sort of either turn your camera on and wave at me, or just break in and start speaking. So yeah, so this first party on high throughput computation, I've started with this slide here, which is the picture is actually an old style computer. In fact, it's an old style high throughput computation back from the days when computers were people.
Chris, okay, I'm not sure that your slide has changed.
Oh, has the slide not changed?
Don't think so.
I'm going backwards and forwards. No.
No.
Can anyone see? So you can't see the second slide yet.
It's just your title slide at the moment. For
Very
me,
strange.
anyway.
Okay. So how about I stop? I'm going to stop the share and try again.
Okay.
Try that. It's good that you told me early on, because I could have.
I was doing something and I turned around and looked, and it's still the same. So.
Yeah. Okay. Let me try and share that again. Okay. So you can see it on the main the
yes
thing, and so let's see what happens. So if I do that, I guess, can you see it changing when I do that?
Yeah, when you do it manually, that's fine.
Okay, so then I'll go to this. So you can probably go back to the main screen now.
Yeah.
Can you see the next? No?
No, still the same.
Very mysterious. Okay, well, there is a plan B. So I can, how about if I grow that screen like that? So if I do it like that, will that work?
Yeah. Yeah.
Okay, it's not ideal because you can see the side. Actually, if I can do that, that's quite close to being how it should be. How's that look?
That looks good.
Okay, good. Right. So hopefully now you can see what I was talking about. You'd have been very mysterious when I was discussing these human computers, but now you can hopefully see them. So yeah. So what we have here is a room full of people who are working in front of mechanical calculators, and they've got little trays in front of them. You can see some of the people there. I don't know. Can you see my pointer? Do you see the pointer? Yeah. So exactly. So this lady here is picking out a piece of paper from her tray. She'll do a calculation, get the result, and put it on the tray on the other side. And then there'll be people running backwards and forwards in this room, picking up the pieces of paper and taking them to other computers and orchestrating the calculation as a whole. So this actually illustrates, high throughput or parallel computation. So you could imagine that each of these computers were working together on a big problem, and that problem was broken down into small pieces, and they're all getting a little fragment of the problem into their in trays. They do a little fragment of the calculation, and then they put it in the next tray, and then the people run up and down between them and collect them together, and then decide who those results should go to for the next step in the calculation. Or alternatively, each of those computers could just be working on their own problem, just beavering away, doing their own problem. And then at the end of the day, someone goes around and picks up all the results from the from the trays, and they have like 100 different solutions or problems solved. So the first version would be what's known as parallel computation, and the second version is what would be called high throughput calculation. So let's try again to turn this screen. So okay, so this is just putting some words to that. So parallel computation, if you're trying to solve a big problem, then what controls the number of processes you can bring to bear on a particular problem is how quickly really you can communicate between those different computers, and then also how much of that calculation you can break down into small chunks. And there's an equation called Amdahl's law, which tells you what speed up to expect given a fraction of the code is not parallelizable. So even if only a small portion of the code is not parallelizable, it provides a limit to how much speed up you can get. So if there's only 1% of your code can't be broken down into small small chunks, then the maximum speed up you can get is a factor of 100. Okay, and it's even worse if 10% of your code can't be parallelized, and that's controlled by this Amdahl's law. I mean, similar effects come from communication costs. So the cost of communicating between the different computers is putting in another factor that can reduce the amount of parallelization you can do. So a solution to this sort of law of this diminishing returns of using a parallel computer to solve a single problem, highlighted by Amdahl's law, is what's known as high throughput computing. So you do many smaller and importantly weakly coupled. So not necessarily completely uncoupled, okay, but at least not depending very much on each other, so that you can send those calculations off and they can do their own thing, and then only from time to time do you have to gather the results back together again. And so this results in a much, this will typically result in a much higher throughput of results than running each calculation in parallel. But it's only really useful if you actually want to do a lot of calculations. If you only want to do one calculation, there's no point doing hundreds and hundreds of the same calculation to get your throughput up. So you have to find particular problem sets or problem types that can take a benefit of this style of parallelization. So one thing you could do that you can use high throughput computation for is to sweep over input parameters for a code. So for example, if you wanted to check the convergence properties of a plane wave DFT code and you wanted to produce a graph of what the total energy was as a function of kinetic energy, then you could do each of those individual calculations for a different value of the plane wave cutoff, do the calculations all at one time, and then gather them together in the graph. So you can sweep over input parameters, or you could sweep over input data sets. So it's another kind of input parameter, but if you're doing a DFT calculation, you'd have to input the crystal structure to your calculations in some input file format. You could, for example, as they did in the materials project, you could take a whole set of those structures from a crystallographic database and do the calculations on all of those structures at once, or at least in chunks. So you get 100 crystal structures, and you just do 100 different calculations on 100 cores, and compute their properties, do geometry optimization, calculate phonons, whatever you're interested in, all at once. So issues that you face when you're doing high throughput calculation is obviously automation. So it's not feasible if you have more than a handful of calculations to be doing those calculations one by hand. Now, I'm hoping that anyone who is doing DFT calculations now are not doing a lot of their calculations by hand. This is very much an old-fashioned way of doing it. Now we'll typically put together job scripts that automate these processes, where one step is done and then another step takes the results of the previous one and does the next calculation. When I started out, pretty much you would be issuing those commands by hand one after another into a computer, but that was because you were typically not doing very many calculations. If you have to do thousands of calculations at once, that's just not feasible. So automation is what is sort of an enabling technology for high throughput computation, be it through simple bash scripts or more sophisticated frameworks that people have developed over the years. Then other issues that crop up are robustness. So when you're running calculations on large numbers of disparate inputs, you need your code to work a vast majority of the time. Now, hopefully, this seems obvious to you now, but certainly historically, it wasn't the case that these density functional theory codes were sufficiently robust that without human intervention, you could just tell it to go on and calculate things, and you could put any input files into them. You would typically find input sets that would cause a crash, and you'd have to adjust a parameter or something like this. So one of the big improvements in these codes, like CASTEP, my code, or VASP, or other similar codes, is their ability to set defaults automatically and to avoid crashing as much as possible. So if it can figure out how to carry on doing the calculation, a good code will figure out how to carry on the calculation. This certainly wasn't the case in the early days. I mean, when I started out with the first version of CASTEP I used, each time you changed the number of atoms in the calculation, you had to recompile the code. So this was a hardwired parameter in the code as to how many atoms you were dealing with. Now, this seems like crazy. Why would you do that? Well, because people were just getting started. They would typically do a few atoms of silicon again and again and again to improve their techniques. But we've got away from that now. The ability to recover from an error if you've encountered one is important as well. And then, very importantly, is that once you've done the calculations, you need to collect the data in some way. So you need to think of file formats or storage strategies so that you gather this data together. And you need to think about putting it in a format that is easy for you to access and manipulate to go to extract further information from that. So in the bottom right-hand side here, I've just put the output of a top command that I ran This was run a very long time ago. I think it may have been on my computer at UCL, or it was my computer before UCL in St Andrews, where I had started building my own cluster for high throughput computation. And I was showing I took this screenshot and made it part of one of my talks to emphasize to people that rather than doing large parallel calculations, which CASTEP was kind of famous for being a good parallel DFT code. In fact, I wasn't doing that at all. I was just doing lots and lots of serial calculations. Okay, so just emphasizing the high throughput versus single parallel calculations. But one thing that was pointed out to me when I showed this with this screenshot was just how long my compute node had been up. Okay, the uptime here was for 134 days. Now, I didn't realize at the time, but this was considered quite remarkable for a computing resource. And no doubt many of you who've used computing resources around the place are constantly being reminded that the service is going down for so-and-so update's going to be done and so on and so forth. Well, one of the beauties of a high throughput computation is that, you know, if you're doing the same calculation again and again and again, so your software stack needn't be very big or complicated. So you needn't have, and it needn't necessarily be connected to the internet for full functionality. So actually, if you're focusing on one particular high throughput task, there's no real need to keep rebooting your entire cluster again and again and again. Those issues come when you have multi-users doing many different activities, and you're connected to the internet, and you have to deal with security. Okay, but from the point of view of computation, there's no real need to do that. And in addition to that, when you're doing high throughput computation, it doesn't matter necessarily if one or two of the nodes fails, because if the nodes fails, you can just pick up that calculation later and do it again. You can just leave the others running. So this is a kind of robustness that high throughput computing can, if it's set up correctly, which means that the cost of compute can be quite low. It could also, if you insist on doing high throughput calculations on, say, the Archer machine, then these very high performance supercomputers, you're probably spending, although someone is spending too much money for you for the kind of compute you're getting. So this is a kind of compute that's cheap and cheerful. You could probably use the Amazon cloud or Azure or whatever to do these calculations. You're doing lots and lots of fairly small calculations without requiring too much memory. So a very cost-effective computing, and I would contend that it's also it gives you very good return on your investment for the compute. So you definitely, either whether you're doing high throughput computing on databases, or you're doing the structure prediction that I'm going to talk about later on, you do discover lots of interesting things, and we found a lot of things over the years with relatively little compute, maybe compared to something like Quantum Monte Carlo, where you spend millions and millions of core hours to get one very accurate number. We get lots and lots of reasonably accurate numbers through DFT. Okay, I'm still having trouble changing. Okay, I've managed to change. Okay, but so the first as I mentioned, the big use of high throughput computing is computing on databases. So databases are maybe your input parameter. The data contained in databases are the input parameters that you can sweep over when you're doing the high throughput calculation. So, for example, the ICSD, the International Crystal Structure Database, or Inorganic Crystal Structure Database, has about, well, I don't know how many it has now. Maybe it's got over 200,000 crystal structures. These slides are maybe a little bit old, but it has over order of hundreds of thousands of crystal structures. The vast majority of them have been derived from experiment. So typically, the only information that's available are the crystal structures. And so one of the opportunities that Gerd Sieder and the Materials Project crowd realized is that these DFT codes could calculate a lot of properties for you. Like, in principle, from quantum mechanics, you can calculate everything. We've not implemented everything in terms of functionality, but a lot have. So this meant that if you had a crystal structure, you could go and fill in the gaps for its properties using computational methods. So this is why this was the sort of impetus behind the Materials Project, and it meant that as an input, it would take crystal structure database, and then it would end up with a rich database with many different properties. Energetics being the obvious one, but potentially other properties. And in the case of the Materials Project, they were very interested in finding new and better battery materials. So they were looking at those particular properties. But you could adjust depending on what you're interested in. You might be interested in photovoltaics or other things. If you're interested in photovoltaics, you'll be interested in band gaps and so on. And you can calculate those for these many crystal structures. So on the right hand side, I've put a few plots of statistics. So the first plot in the top left hand corner, number of atoms, is telling you how many atoms in a unit cell the crystal structures contained in the ICSD have. And so it's a sort of essentially a histogram or just a plot of the frequency. So it's saying that for there are about 500 structures with one atom in a unit cell in the ICSD. I guess lots of cubics, FCC or simple cubic or BCC structures, and so on. It seems to reach a peak around in terms of the number around 10 atoms. So 10 atoms per unit cell is a very common number. And by the time you get to about 100 atoms per unit cell, you're nearly done. There aren't very many structures in the ICSD with more than 100 atoms in a unit cell. There are some, but there are not too many. And actually, this is an important plot because it tells you, it kind of explains why high throughput computation coupled with density functional theory calculations really took off. Because DFT calculations, the plane wave DFT calculations like that you might do with Cassidy and VASP are really good for crystal structures with about 100 atoms in a unit cell in terms of time. It's very efficient. You can do those calculations rapidly and efficiency. If you push it onto a big computer with plane wave DFT codes, you can get up to 1,000 atoms or maybe even beyond, but you're not going to do that very often. So the sweet spot for doing plane wave DFT calculations is about 100 atoms in a blow. And that just happens to be catching most of the ICSD crystal structures. The other thing to note is the plot on more to the right hand side is the frequency of the number of different species in the crystal structures. So if you only got one species in a crystal structure, that's an elemental crystal structure. That's like pure carbon, graphite, or diamond. And then if you have two, you're in the binary systems. You've got two different atoms. And then as you go to 3, you get ternaries, and 4 quaternaries, and so on. And you can see here that there's a peak around the ternary, binary, ternary, quaternary system. So most crystal structures that you encounter have 2, 3, or 4 atoms of different type in their unit in the unit cell. There are some with larger numbers, 5, 6, and 7, but very few above that. And on the bottom right hand side, I've put a plot of what kind of elements might they be, and this is more looking at the Earth, the abundance of elements in the Earth's crust, and so it's a log plot with atomic number, and so the green atoms you can see are the common atoms, and not coincidentally, they're the atoms that make up the rocks or dirt that we walk on every day on the planet because they're common, they're everywhere. So the carbon, the silicon, the oxygen, the magnesium, the potassium, phosphorus, and calcium, the rock-forming elements. And at the bottom right-hand side, we see the so-called rarest elements, the golds and platinums that we don't often stumble on when we go for a walk outside. If we do, we'll probably be quite happy. And these are rare elements. But my point here really is that, well, there's different points you can take from this graph. So if you're interested in sustainable chemistry, you would be interested in looking at all the possible materials that you could make from the rock forming or common elements. But if you actually look at material science and industrially important elements or materials, you find that actually all of these elements that are on this plot are important. Even platinum is widely used in catalytic converters in cars. Gold is used either in jewelry or in electrical circuits. Palladium, rhodium, etc., also used for industrial purposes. So actually, we really need to be able to treat around 100 or 90 different elements well if we're going to be doing relevant DFT calculations. So that means we have to have good pseudopotentials for all of those elements. And I mentioned briefly at the start, that was something I was responsible for the CASTEP code. So this is a sort of a hidden technological enabler for everything that people are doing with DFT codes now, is that before you tended to do a project and you'd have a crafted pseudopotential for that particular project, and then maybe someone else wanted to work on the same element and then or same system, and so you'd share that potential with them, and it would be sort of word of mouth spread of these potentials, which meant that if you were suddenly asked to do, I don't know, bromine selenide or something, you probably haven't got the pseudopotentials to do that, so it would take you some time to get that data. So something that really useful that was done also in the throughout the early or 2000s was the development of databases of potentials. So CASTEP has a database, VASP has a database, Quantum Espresso has a database, and you shouldn't. Although I was responsible myself for that, I don't think I'm overemphasizing that. These are an important part of the DFT methods. Without those pseudopotentials, without those reliable pseudopotentials, you'd be quite restricted as to what kind of calculations you could do. Now, the other issue is that many industrially important materials are actually transition metal oxides, and ordinary DFT doesn't really treat them very well. So they're strongly correlated. DFT is not properly treating the localization of the electrons in the 3D or the 4F electrons. So again, if you want to do realistic, useful materials, you've got to confront that. You can't say, I just will ignore any transition metal oxide, because you'll be ignoring most of what's important. So particularly, for example, the battery cathode materials, cobaltates or nickelates or all these different materials, they involve, they are strongly correlated systems. And this was actually one of a really important contribution that Gerd Sieder brought into the materials project. And this was a sort of careful and systematic use of GGA plus U. So GGA with a Hubbard's U to approximately treat this strong correlation. Now, this is kind of it is an approximate. It's not a perfect solution to the problem of strongly correlated electrons. Maybe you need to go definitely beyond DFT, dynamical mean field theory, or other more exotic techniques to properly deal with this. But GGA plus U or LDA plus U is a good compromise. So it allows you to get quite a lot of the properties of strongly correlated, particularly magnetic systems, without a dramatic increase in the cost. So yeah, so in the materials project, particularly in the battery materials, there's a lot of discussion about calibrating and using these Hubbard U's. So one final wrinkle is that if the state is magnetic, then you have a challenge in that many of the systems might be ferromagnetic, but many might also be antiferromagnetic, or they might have a more complex spin pattern. So you have to do something about determining the magnetic state. It's quite common for people just to assume everything is ferromagnetic, okay? But that probably not sufficient, and probably be increasingly recognized not to be sufficient as time goes on. So, okay, so once you've done these calculations, you need to store them in some way for analysis and sharing. Hence, origin of things like Nomad or Materials Project, or the many other databases that are out and about there now. So let's get to the next page. So in order to share data, you have to think about how to file formats and how to communicate that data. And another important feature as well is, or part of that, is so-called metadata. So metadata is data about data, and it allows you to communicate how you did a calculation. Where did you get the crystal structure from in the first place? What codes did you use? When did you do it? What settings and parameters did you use? Because without that, the data is nearly meaningless, because no one, it might mean something to you because you know what you've done and you're able to keep your calculations consistent. But if you want anyone to take that data and use it for anything else, it's not useful unless they know how you arrived at that data. What did you use, at LDA or GGA? That's kind of important information. That will give you that will tell you whether you can compare the data that you have with a calculation that's been done with, say, LDA. You need to know that it's been done consistently. The same applies if you're doing an experiment. So if you're doing an experiment, when you do your experiment, you should also record the details of the experimental setup. If you've got an X-ray diffraction pattern, you need to record what wavelength of X-rays you use, so that people can interpret those patterns. So in the case of DFT calculations, metadata that you might want to record might be things like the version of the code, compilation details, the pseudopotentials, basis set, like plane wave basis set or other, Brion zone sampling, which density functional theory you used, and so on. And so you need that for comparison. And on the right-hand side, I'm just showing you an example of the file format that I adopted and developed for my structure prediction works. This is one of my formats. It's a .res file format for the AIRS structure prediction code. It's based on a res file format from the ShellX crystallography software suite. I chose to adopt it because many crystal visualization software packages automatically read this file format, and at the same time it was sort of a minimal and easy to use file format. So it just records, the lattice parameters and the positions of the atoms. And that's the key data. It has a title line which allows you to record some of the metadata, and also allows you to have rem comments, so reminder comments that allow you to add further metadata. So in this example here, the black text is file format related stuff. So that's telling you when the file ends and when it starts, and whether it's a reminder that you're going to get lattice parameters data, that what kind of lattice is and what kind of chemical species you have. So that's a given the file format. And then you have the blue numbers, and this is actual data that's derived from the calculations. So these blue numbers have been computed in some way. So that's the data. And then the red stuff is all the metadata. So we have a name for the calculation and data when you did it, what version of CASTEP you used, and so on. So so this is a key part of giving value to your data and allowing you to share it with others. There are other file formats. There are other approaches, frameworks for collecting data and managing it, but you need to do it in some way or other. Once you have decided on a data file format and a system, that's the most important thing. You don't need to worry necessarily that you're not using exactly the same file format as someone else, because if you've got a defined format, you could always convert from one to another. There might be certain attributes that are missing, but if you've got one file format, you can typically you can write a converter to convert to others. All right. So what's the key and the most important property in high throughput or even structure prediction calculation is the thermodynamics of the system. So the most important thing that we want to know is whether something is stable or not, or if it's not stable, how would it change to become stable? So that's thermodynamics, and the key variable there is the Gibbs free energy, which is shown on the right-hand side. So that is the potential. It's the thermodynamic potential that's minimized when a system reaches equilibrium at a given pressure and temperature. Now, thermodynamics is an equilibrium theory, and that equilibrium might actually never be reached in the time that the universe is around. So your system might be stuck in a metastable state, but it's still important to know that it is indeed metastable and not the most stable. So thermodynamics, it's sort of a first step energetics of a system. If you want to understand more about pathways and synthesis or growth of materials, then you get into the world of kinetics and so on, which I won't discuss in this at all here. So everything I'm going to be talking about is going to be focusing on what would be the ground state of the system in the fullness of time. Okay. That's a good starting point. So the enthalpy H, which is part of the Gibbs free energy, is really easy to calculate. That's just the internal energy of the system, which is output from codes like CASTEP and VASP, plus a term which is the pressure times the volume, PV term. So when you're evaluating the enthalpy, say you have a structure from a database, it's important to at least relax the positions of the atoms. So relax means move them so that the atoms have moved to their lowest energy in the particular level of theory that you're looking at. Because often, well, for various reasons, the structures from experiment, they might be correct, okay, but they'll often be at finite temperature. So the lattice may have expanded in some sense, and the calculations we're going to do, at least to start with, they're going to be at zero temperature. Or sometimes there's just mistakes in where the atoms have been placed in the in the experimental analysis of the results. So relaxing them with DFT actually can, in many cases, give you better structures than you would get if you took them raw from the experimental data. Not because the experiments are wrong, but because they've been maybe interpreted slightly incorrectly and atoms have been put slightly in the wrong place. This particularly applies to if you have hydrogen atoms in your system, because hydrogen atoms are light atoms. And it somewhat shocked me to discover that for all these crystal structures I was downloading from databases, when they contained hydrogen, very rarely were they actually being experimentally measured in the positions that the crystal structure had them. Typically, the experimentalist will solve the crystal structure based on the heavy atoms and then just paste in the hydrogens at roughly the right distance from the other atoms. So in many cases, you can detect that when you find that all of the hydrogen atoms are exactly 1 angstrom away from the atoms. You think, oh, there's something a bit fishy going on here. So if you relax them in DFT, you'll probably get a better result. We found this was very important when we were computing NMR chemical shifts in solid state NMR. The NMR calculations and experiments were so sensitive that you could easily tell if the X-ray structure was not at a sufficient level of quality. So the agreement of the NMR with experiment improved when we relaxed using DFT. So as well as moving the ions, you can also relax the shape of the unit cell using the stress as well. So if you've calculated the enthalpy, and let's just put the entropic type part to one side for the time being, then the first thing you can do when you do a high throughput calculation is do some ranking of the crystal structures. So which is going to be the most stable polymorph, which are metastable polymorphs, and so on. You can also use the relative free energies to tell you the direction of a particular chemical transformation. So you can calculate based on crystal structures from the ICSD, and you say, well, this plus this, would be exothermic to form compound C, or in this case here, A plus B will form AB in some way. I heard a bing. Oh, what is something has come up saying participants can now see my application. I don't know what that means. Is everything okay for everyone? Yeah. Okay. I'll keep going then. So yeah. So while applying pressure is easy, you just need to multiply pressure, the target pressure, by the volume of your system to add it to the internal energy to get your enthalpy. Evaluating the effect of temperature through entropy is much more challenging. Okay, so strictly, if we want to calculate a full phase diagram of a system, we need to know what the entropy is. And in general, computing the entropy of a system is much more difficult than calculating the internal energy. But there are ways of estimating it. And so at low temperatures, well below the melting temperature, so when the atoms are not significantly rearranging due to the thermal motion, then you can make a an approximation known as the quasi-harmonic approximation to capture the vibrational entropy. And also on top of that, the quantum zero point energy. And so this is just based around the idea that around a minimum, you can always expand an arbitrary function as a quadratic function, and then you calculate the vibrational modes in that harmonic potential. Okay, and that leads to phonon band structures and so on, which I hope you've heard about already in this course. From the point of view of calculating the free energy, we really just need to know what the entropy of those vibrations are, and then we multiply that by T. And then we add that to our enthalpy, and then we've got the Gibbs free energy. Now, just so the easy approximation is to do the harmonic approximation. In many, if not all cases, actually the potential is not harmonic. It deviates from harmonic and has anharmonic contributions, and these can be significant. And more advanced methods actually now take those anharmonic terms into account, but it's much more work to do it. So it's relatively easy to calculate nowadays the vibrational free energy through the quasi-harmonic approximation. You've got to really want to do it if you want to go to the anharmonic level. So that's one kind of entropy. We can do vibrational entropy. Another kind of entropy which we can do sometimes, well, it comes under the heading of configurational entropy. In the case of mixing of elements on, say, a fixed lattice, then you can just enumerate what the entropy will be. So I've given an example here where we've got a simple square lattice of A and B, A red and blue B, and then I then examine what the entropy of mixing would be, and then I can find the Gibbs free energy to compute whether a particular mixing will take place or not. And this is just based on permuting the identity of atoms on a lattice. This happens sometimes. This is the foundation of dealing with alloy formation and so on. So if you're forming an FCC alloy or a BCC alloy, that's all something you can handle. But that's a kind of special case. In general, atoms configurational entropy is much more complicated than that. It involves actual movements of atoms off their particular lattice site. An extreme example of that is melting. So when you heat a lattice up, at some point the atoms start moving around off their sites, and any harmonic or quasi-harmonic approximation is simply going to fail. So in order to handle that case, the case of melting, you have to do thermodynamic integration. Maybe you've been introduced to that in your in this course already. So these are sophisticated techniques using molecular dynamics to basically by taking certain reference systems, approximately good reference systems, using either molecular dynamics or sampling methods to evaluate the entropy of mixing, or even just more general entry of melting, or even just general larger, far from harmonic motions of a system. So anyway, so entropy is difficult if you go beyond vibrational entropy, but increasingly techniques are available to help us do that. So the next thing I want to talk about, and this might seem like something that's come a bit from left field. I'm going to introduce this concept of convex hulls. So convex hulls are they're a set of points. A convex hull of a set of points is the smallest convex region that contains the points. Or if you want to imagine it physically, if you bang a bunch of nails into a board and then stretch an elastic band around those points, the convex hull are the paths that the elastic band take as it fits itself around the outermost pins or nails. So you can see that example on the top right hand side. I'm showing an example of a bunch of I've scattered a bunch of random points in 2D. I've stretched an elastic band around it. This ellipse is an imagined stretched elastic band. I've let it go, and then it's picked out the convex hull of those points. So in 2D, it's easy to imagine this. This idea extends to higher and higher dimensions. Maybe harder to imagine an elastic band in 4 dimensions, but it's actually can be dealt with using computational geometry algorithms. So you can specify an arbitrary number of points in an arbitrary dimension, and there are computer codes that will return back what the points on the convex hull are. Okay, so this is something that we outsource as so I would never write a code for computing convex hulls and for anything other than for hobby reasons. I think there are plenty of experts in computational geometry out there that provide these techniques. So why are we interested in this? Well, this comes to one of the key uses of thermodynamic data when you're doing high throughput computation, and that's the assessment of stability of different compounds. So there is a construction, and it's also known as the Maxwell construction, which allows you to graphically identify which are the stable compositions of a particular chemical system. So, for example, on the right-hand side here, I have computed a convex hull of a selection of compounds involving caesium and iodine. Okay, and the procedure for doing this is that you calculate, or in your high throughput calculations, you know what let's say that the enthalpy, or it might be the Gibbs free energy, but in more cases it'd be the enthalpy for each of these different crystal structures with different compositions. So you can see here the red, the caesium iodide has got a ground state structure And it's also got a couple of metastable structures as well. Okay, you can see maybe if you look closely, there's some other metastable cesium structures. For the other compositions, it seems that we've only got one for each. Oh no, there's two for the iodine as well up here. There's a red spot there as well. So what you do is you take the most stable structure that you have for each of the end members, in this case A or B or cesium and iodine, and then you compute the formation energy for each of those other compounds. So to calculate the formation energy of cesium iodide, you take the energy or the enthalpy of cesium iodide, and then you subtract it, because it's got one cesium and one iodine, you subtract it by one unit of cesium energy, so the energy per atom of cesium, and then you subtract one for the iodine, and you're looking at the difference. And if the difference is negative, then that reaction is exothermic and it will want to form. So that would be the formation energy. You do it for all of your different compositions and structures. And then what you plot is the so-called normalized formation energy. So this is an important point. It has to be normalized. You have to divide the formation energy by the number of components that went into it. So in the case of an element, cesium, you calculate the energy of the formation energy of cesium, which is cesium minus 1 times cesium minus 0 times iodine, and then you divide it by 1 because there was only one cesium in it. Okay, well, that was 0 anyway. It was 0 anyway because you just subtracted cesium, the energy of cesium from the energy of cesium. Same for iodine. In the case of cesium iodide, you are going to divide by 2 because there's cesium and iodine that you've combined here. And in the case of cesium iodine 2, you divide by 3 and so on. And that's the normalized formation energy. So if you plot that as a function of the composition, so it's 0 if it's purely, so X is 0 if the compound is purely cesium, and X is 1 if it's purely iodine. So X as in A1 minus X, B of X. Okay, so you plot that graph, and then you construct the convex hull. So you stretch elastic bands around it, you let them shrink, and then it just touches this point, this point, this point, and of course it touches the end members as well. And if it was really a convex hull, you'd also have a line going across, joining the cesium and iodine across the top as well, but that typically is not plotted. And so then you look at the points that are on the convex hull. So you've got cesium iodine on the convex hull, also cesium iodine 3 and cesium iodine 4, and so on. And so these are the stable compositions. These are the compositions that that are thermodynamically stable, in contrast to, for example, cesium iodine 2, which is above the convex hull. Okay, and structures above the convex hull could lower their energy by decomposing, in this case, into some cesium iodine and some cesium iodine 3. Okay, so you would take 2 cesium iodide 2, it would split into 1 cesium iodine and 1 cesium iodine 3. Okay, so compounds above the convex hull are unstable to decomposition. And so you can see this is a super neat way. You quickly calculate the energy of, say, a whole database of compounds for a particular chemical system. You download them, calculate the energy, and you just plot them in this way, and you're able to predict which are the stable compositions. Now, of course, this is not taking into account any kinetic factors. So it's not saying that this is, if you mix these up in the lab, that you would immediately form these compositions. But it would say if you were able to sufficiently anneal the system over a long enough time, that would be the thermodynamic composition. So you can extend this to ternary compounds as well. So here's an example for strontium, calcium, and oxygen. So for calcium titanate, famous perovskite material, in this case here, I just downloaded all of the compounds from the ICSD containing calcium, titanium, and oxygen, calculate the energies, and then follow this procedure for computing the convex hull. This time, because it's got 3 compounds, we form this ternary plot, this triangle ternary plot. So you go from 0%. So here you got 100% oxygen, 0% calcium, 0% titanium. And then here we've got 100% calcium, here we've got 100% titanium, and in the middle somewhere we've got calcium, titanium, oxygen as the mix. And so all the different compositions are around here. And I'm plotting here, the circles here are the stable compositions. And we found a bunch of stable compositions along the titanium to oxygen axis, and just one in the ternary space here, but also some metastable faces nearby. what you can also do is do a sort of what's known as a pseudo-binary slice, where here we go, this is calcium oxide, CaO, and this is titanium dioxide. And we can think of titanium dioxide and calcium oxide as our A and B for a normally a binary convex hull calculation. And that's what's plotted here. And so you can see more clearly now here, we've got a binary calculation. This is pure calcium oxide, this is pure titanium dioxide, and here we've got calcium titanate. And you can see the metastable phases here and some nearly stable phases here, but they're not on the convex hull. So given thermodynamically, they are unstable to decomposition, but they're so close that probably they could be formed. They could be considered metastable. Okay, so when we put everything together, we can actually, if we start computing the free energy using temperature, using either the quasi-harmonic methods to calculate the entropy of vibration or thermodynamic integration, you can start to map out phase diagrams. So here's on the right-hand side is an example we did for hydrogen at high pressure using structure prediction, which we'll talk about later. We identified what the likely or possible stable phases might be, and then we computed both the quasi-harmonic free energy and also 0-point contribution, which varied according to temperature and pressure, and then we just map out which is the stable phase at each of the pressure temperature pairs, and that maps you out a phase diagram. The dotted lines are showing some error bars on that as well. So what this is, I'm not sure if you've heard of it, but in material science, a very famous technique is known as CalFAD. So it's calculation of phase diagrams. So CalFAD is the traditional way of calculating phase diagrams, and it largely uses empirical data from experiments that are interpolated in some way to allow you to move over the whole pressure temperature range. But they're largely done from experiment. More modern versions are partly augmented by calculations. Whereas what I'm showing here is a purely computational way of calculating phase diagrams, but it's a kind of CalFAD. It's calculation of phase diagrams, but it's doing it from a DFT way all the way through. Let's see. Yeah. Okay. So thermodynamics is probably the key thing that you want to discuss when you're doing high throughput calculations. It tells you whether things are stable or not. But actually, if you're a material scientist and you're trying to design a new material, it's not interesting. It's not interesting per se whether something is stable or not, unless it has interesting properties. So it's actually the properties of the materials that are most interesting. And in principle, we can calculate these properties using quantum mechanics. But in many cases, these calculations are difficult and possibly unattainable with sufficient precision. So if you're doing a high throughput sweep or search for a new material particular property, it's not necessarily the sensible thing to just try and compute your properties as accurately as possible from first principles, because in that case you might not perform very many calculations. It might be so difficult that you only calculate it for one structure, and so you've had no chance to explore the other possibilities. So if you're doing these kind of high throughput sweeps, it's important actually to think of what an overall figure of merit for your system, and ideally a rapidly computable descriptor or proxy for the quantity. So for example, you might think if you're trying to find a hard carbon material or a hard material, you might want to try and maximize the density or the number of bonds per unit volume or something like that. That might be a good proxy for hardness, which is otherwise difficult to compute. But how well your search goes will depend on the quality of that descriptor. If your descriptor is missing all the good ones, then you're not going to be as successful as someone with a better one. So this is where it's challenging to find the right easy to calculate descriptor. An area where maybe it's relatively easy, for example, is photovoltaics, where a lot of what you're interested in is band structure. And these are something we can calculate rapidly and fairly accurately using first principles and beyond methods. So I highlight here that what you would typically do is a broad sweep with maybe a cheap but lower lower quality descriptor, just to get an idea of what might be good candidates to consider further. And then when you considered some likely hits or successful ones, you might then focus in on those and do much more involved calculations. And if anyone is interested, we recently published a project along these lines when we were looking for high temperature superconductors under pressure. And we did a sort of hierarchical approach where we did a rough calculation of whether something might be a superconductor first. We trained a simple machine learning model to guess a little bit better which ones might be superconducting. And then if it looked like it was a good candidate, we went the whole hog and we did a careful calculation using quantum espresso to calculate the full electron phonon properties to assess what the TC would be. So this is a very hierarchical approach. So I think this is just the last bit for this section. This is really just to point out that when you're trying to optimize properties, you're always balancing multi objectives against each other. So you tend not to say, I want the hardest possible material or I want the strongest possible material. You're typically saying, I want the strongest material that is cheap enough that I can afford. Oh, I'm getting a message up here. Okay. That's fine. So you're in the world of multi-objective optimization, and so an example I gave here is if you want a photovoltaic might have to have a band gap around 1.3 electron volts, be chemically stable, and have low environmental impact and be cheap. So you got multiple objectives there that you have to satisfy at once. A tool for assessing multi-objective optimization is something known as the Pareto front. And so I've given an example here of a Pareto front for carbon, and I've got a set of carbon structures. The properties that we're optimizing here are a bit fake. It's energy and volume, but it's just as an example. So I've plotted the energy and volume data for carbon for a bunch of different polymorphs. And then I want to have a stable but dense structure. Okay, well, stable but dense structure is a movable feast. How important is the denseness, or how important is the stableness? So if I really care about stableness, I'd be interested in the graphite structure. It's more dense than these structures up here and more stable. Okay, if I was really interested in denseness, then I'd be driven to this simple cubic phase of carbon up here. It's rather unstable, but it is the most dense structure that we have. Now, the idea behind the Pareto front is that these points, points here along the yellow line are on the Pareto front, whereas these points here, they're not on the Pareto front, and they're known as dominated by the Pareto front. So each of these points here are dominated by the Pareto front, in that you can find something that is better either in terms of energy or volume than this point here without making any compromise. So there's just no point considering any of these structures. These structures are less dense and less stable. And these structures here again are less dense and less stable than diamond. So the diamond dominates all of these points up here. So this can be extended to higher dimensions as well. And here's just an example from a paper where something like this was being done, actually for looking for hardness versus energy. So here we're saying we want to maximize the hardness of the compound and have it as stable as possible. And the end result was, well, you can't do better than either diamond or graphite or diamond are basically your options here. And they didn't manage to find anything that beat those. Okay, I'm going to stop my share now. That's the end of the first section. I'm keen to just have a couple of seconds to grab a glass of water before we move into the next section, but I won't be any longer than that. So does anyone have any questions now on that section? Yeah. Okay, you can think about them. How about you think about them for a few seconds and you can pop them in the chat, so when I come back I'll see them. I'm just going to grab a glass of water and I'll be back in a few minutes. Okay, I'm back. I don't see any messages. I'm going to share the next. So maybe it's a good idea just to keep pressing on. Is everyone there? I can't see anyone. I better not start if everyone else has gone for a coffee as well. You can give thumbs up if you're there. You can't really do it if you're not there. Okay, I've got a couple of thumbs up, but maybe not everyone. I'll wait a couple of seconds. Okay, another thumbs up. Okay, so shall I start? Does anyone? I can't see anyone. So if someone will show me some signs of life, I'll get started. If I don't see signs of life, I won't be able to start. Anyone pop their camera on just to show me that there's a real. Ah, okay. Yeah, we got at least one real person. So I'm happy to start if there's at least one real person in the audience. It's not much fun talking to nobody. Okay, so this next section is structure prediction, and it's something I've actually been involved in myself in developing a lot of the methodologies some of the methodologies that are used at the moment to do first principles structure prediction. So this picture here actually is on the title page. Was the result of research I did while I was at UCL with Angelos Michailidis, who I think you heard from last week or previously when we were both together, where we're using structure prediction techniques to predict new two-dimensional phases of water ice. And so the technique that we used to do that is called AIRS, and I'll explain that method later on. In the context of other approaches that are available as well. But the basic idea behind structure prediction is anticipating what structure a bunch of atoms will adopt. Okay. Often it's often talked about in terms of crystal structure prediction, so with a focus on crystal structures, but structures needn't be crystals. They might be defects, they might be interfaces, and indeed a lot of the work that I've done has been on these non-periodic systems such as defect and interfaces. Now, I just wanted to pointing out at the bottom here that this idea of structure prediction is as old as modern atomistic sciences itself. So so this chap here, Van Hoff, was, I think, the first Nobel Prize winner of chemistry back over 100 years ago, and he wrote a book or many articles on this concept of the arrangements of atoms in space. And he was the person who was responsible for the idea of carbon having tetrahedral bonds, or the basic building blocks of organic chemistry. And so in a way, that was his theory. His theory was, how you would plug carbon atoms together and what structures, what angles they would form. And he took that a step further to do some of the first structure prediction, where he predicted the structure of some small molecules. These are allenes that are given in the bottom left-hand side there. So at each time, as scientists, we've developed a new theory for describing the interactions or the forces between atoms. These have been used for structure prediction. So right from the very beginning, where it's just in terms of angles and bond lengths, to a more sophisticated interpretation of those ideas in terms of force fields or molecular mechanics, to what we have now, first principles methods and density functional theory. They've all been used for structure prediction. Of course, as we go up the level of theory, we're getting greater and greater fidelity with reality or nature, so more chance of what we're predicting to actually be to be true. So as a whole, crystal structure prediction or structure prediction as a whole is been considered a difficult problem. Okay, and it's so difficult that it actually prompted an opinion piece in Nature in 1988 by John Maddox, who was a very famous editor of Nature and opinionated editor of Nature, who's pointed out that it was a scandal that we weren't able to predict the crystal structures of solids just based on their constituents. Now, there were even people in 1988 who actually said, no, we couldn't predict certain crystal structures from their constituents using theoretical methods, but it certainly wasn't widespread or routinely successful. With recent advances in these sort of first principles calculations of energies, this is allowing us to do a much better job. Now, there is a very famous area of crystal structure prediction, which is molecular crystal structure prediction. And this is of great interest because these small molecules, small organic molecules, are related to pharmaceutical compounds, and pharmaceutical companies care very much exactly which polymorphs these small molecules adopt. So there's been a big effort over many, many years to try and perfect our ability to predict the crystal structures of organic molecules, and these undergo so-called blind tests every 5 years or so. There's another one going on at the moment. And there are people who are really expert in making these predictions. And in 2015, there was a news article in Nature following up from that last blind test, where Nature basically admitted that it was now kind of a solved problem, in that we can now, no matter what John Maddox said, we can now predict the crystal structures of molecular crystals. I'm interested in something a bit more general than that. I am interested in molecular crystal structure prediction. But because what I'm doing is what I'm interested in is first principles methods, in principle, I should be able to, it shouldn't matter to me whether a crystal structure is organic or inorganic or hybrid or whatever, and they're just atoms. So there's a human distinction of these different types. So by taking a first principles approach, we may not be the fastest at doing any particular method. You'd probably be, if you were able to craft a bespoke force field for an organic molecular crystal, and you did well at that, you're likely to be able to do crystal structure prediction better and faster than with the first principles method. But if suddenly I said to you, yes, now take your molecule and squeeze it to the pressure at the center of Jupiter, your force fields probably wouldn't work anymore, and you'd not have much chance. Whereas if you had a first principles approach, this would still work. And exactly that's the kind of things that I'm interested in. And so in general, inorganic materials. So take random selections of those 90 atoms of the periodic table, put them together, and what crystals will they perform? Will they adopt? So I'm just going to sort of highlight a few different approaches to crystal structure prediction that are around, and then I'll finish off by talking about my approach, or ab initio random structure searching. So this one I call ancient knowledge. This is what people used to do for crystal structure prediction in sort of physics or solid state chemistry. And so the basic idea is that it is observed it's been observed that there are many repeatedly crystal structures adopt the same structure prototypes. So you get the same structures again and again and again. So it might be rock salt structure, NaCl, the structure of sodium chloride, or it might be a BCC lattice or whatever. These structure types, they come up again and again. So if you come up with a new compound, an approach you can do to structure prediction is to just try all these structure types, substitute your elements in appropriately, and calculate the energies or free energies using density functional theory, and then rank the results. So this is traditionally known as rounding up the usual suspects. So you just gather together all the known structure types that are common, diamond structure, and so on and so forth. Put your elements in appropriately, calculate the energy, see which is the most stable. And that's what there are many examples of crystal structure prediction being done in that way. Sometimes successful, but many times using a more modern techniques found to have been wanting. But they have been given, this approach has been given a new lease of life through sort of database or high throughput approaches. So now we have a database of structures. We don't need to be restricted actually to the usual suspects. We could actually, for example, if we were interested in a compound with composition AB3, as I've got on the right-hand side here, we could go through a database and pick out every AB3 type compound that is there. So aluminium AlCl3 all the way to bismuth iodide or iodine 3 and so on. Pull out all those structures, substitute A and B appropriate, and then calculate the DFT. And there might be 1,000 such structures. It's not a problem because we've got high throughput computing now. We do that, and then yeah, we'll probably make quite a good structure prediction. The problem with this approach is that it will work brilliantly and be very quick if the structure that you're interested in, has already been seen before. If the structure type has been seen before, then it will be in the database and you'll be able to pick it out. But if you've come across something that is genuinely new, then it will just fail completely. And so a lot of what advances beyond this approach to structure prediction are about trying to find new structures. So probably the most obvious approach you could think of is, try and do it the way that nature does it. So nature, has no trouble crystallizing materials. Well, it has troubles crystallizing some materials, but many materials crystallize just fine. So long as you give, for example, a planet a few billion years, then the atoms can settle down into their various mineral structures, and the universe has sorted that out. So along that lines, in principle, because we know the laws of physics that describe atoms in the Earth, we could actually simulate that process. We could put the same types of atoms in, do a molecular dynamic simulation, and just wait for the structures to crystallize. But there's problems with that. Not least being the problem, the timescales of crystallization are very, very long. And you will have seen already in this course that when molecular dynamics are being performed, especially from first principles, the lengths of the molecular dynamic calculations might at most be nanoseconds. They're typically picoseconds in length. But if anyone has any experience of crystallizing, I don't know, sodium chloride or copper sulfate when they were kids at home, it would typically take days to grow those crystals. So the basic timescale for crystallization is seconds or days or years or millennia, and the molecular dynamics are doing nanoseconds. So we're just not even in the same ballpark. So actually that makes the idea of doing crystal structure prediction entirely using molecular dynamics, it's just not going to work. You might be able to find, and indeed there are examples of crystal structures having been predicted with molecular dynamics, if the crystallization process is very quick for whatever reason, or can be forced during the calculation. But in general, it's not a useful approach. So the technique that's used to try and make this more realistic or more likely to work is so-called metadynamics. So metadynamics is a way of basically forcing certain areas of the energy landscape to be searched or explored during a dynamic calculation, or at least stopping your system visiting certain regions of configuration space. And effectively, what you do is you determine some reduced variables or reduced parameters and force the crystallization to happen. So, for example, you maybe control the lattice parameters and force the lattice parameters to become cubic or take on the particular symmetry that you're interested in. So this can be used. There's an example here from Artem Oganov looking at magnesium silicate polytypes using metadynamics. The difficulty or the limitation of this approach is that you always end up fairly close to where you started. So if you've got a particular crystal structure type and then you start heating it up and doing metadynamics, it wanders, but it only wanders around in the nearby regions of configuration space. So you can see this example here. These NGSIO3 polytypes, they're all based on SIO6 octahedra. So nothing dramatic changes in terms of the bonding and so on. They're just different rearrangements of those octahedra, which in this case was very useful. That was the space that you wanted to explore, but in general, you could miss out on some more dramatic phase transitions. So the next approach that you could try is to use, you could appeal to Darwin. So we've done Newton, we'll now do Darwin, another Cambridge scientist. We try and evolve or breed our crystal structures, and this is the behind the idea of so-called evolutionary algorithms. And you'll see actually the evolutionary algorithms and my random search approach, along with others, they all kind of emerged about the same time, around 2006. They started to become published. So Matt Probert, Artem Oganov published Evolutionary Algorithms for Crystal Structure Prediction. Same year, the Avenatio random structure searching came down. The ideas are very similar. They all start with the idea that we're going to have some randomness in the way that we generate our structures. So you start with some random structures. Now you'll see later on with airs, we never finish with the random structures. We just use random structures of particular type. Whereas in the case of evolutionary algorithms, you start randomly, or possibly using some seed structures that you know are good structures already, and then you progressively build new structures from those. And and how you choose how to build the new structures, you base it in some sense on the fitness of the structure. The survival of the fittest. In this case, the fittest typically will be the structures which are the most stable. So the most stable structures are would be defined as the fittest ones. And so in order to get the next generation of structures, you'll maybe generate 20 or 30 random structures. You'll relax them with CASTEP or VASP. You'll see what the relative energies of those structures are, and then you'll pick out the ones that are the most stable, the lowest energy ones, and you'll say, okay, maybe we want to combine those two structures together. We'll have a bit of that one which was quite stable and a bit of another one that was quite stable, and we'll splice them together, and then we'll take them to the next generation. We do this multiple times with multiple random splicing together of the structures. It's easy to say in words, what you do. I think if you think about it for very, very long, you realize it might not be quite so straightforward to know how to breed a new crystal structure. How do you cut a crystal structure and stick it back together again in a meaningful way without making the energy of the structure ridiculously high? And indeed, it's that kind of the way that the structures that are evolved, which is the key details of these evolutionary algorithms. So one of the challenges so as I say, one of the challenges is designing these ways to breed the sensible structures. The key, and typically these methods end up with a large number of different parameters to set up the calculation. So you're going to do a calculation. I mean, now things have matured a lot. I think there are a lot of preset parameters that you could use that have been found to work well. But certainly in the early days, it wasn't immediately obvious what parameters to use. But one of the challenges actually is maintaining diversity in your population. A general problem in society, but also when you're doing evolutionary calculations, because it turns out that if you find a particular structure which is very stable, then these evolutionary algorithms it's very fit. So just even though it's not the best structure, it's pretty good, and it just keeps making more and more of that structure. And it's sometimes referred to as a sort of cancer. Everything becomes the same in these calculations. And so quite a lot of effort is done in terms of what they call niching, or employing diversity to these algorithms, which means thinning out the repeats, making sure you don't get the same structure again and again. Anyway, so for my taste, these algorithms are a little bit intricate and complicated with a lot of parameters, but there's no question that they work very well, and there's been a large number of very successful applications of these algorithms over the years. So another approach, which I find slightly more appealing, and this is, we're going outside Cambridge here to Boltzmann and statistical mechanics, and it's looking at a sort of statistical mechanics kind of approach to doing the structure prediction. And so there are, sort of the most famous StatMech inspired algorithm for global optimization is known as simulated annealing. And simulated annealing is an algorithm by which you start with your system in some highly hot or high temperature state, and then you have a profile of reducing that temperature, and your system is jiggling around at this high temperature, and then as you reduce the temperature, it slowly settles down into the global, hopefully the global minimum. Other sort of related algorithms are known as basin hopping or minima hopping, and these are very effective algorithms if you happen to be in what's known as a funnel structure in your energy landscape. So on the right-hand side here is an example of a funnel energy landscape. So if you imagine you starting at the blue point here, and then so all of these algorithms work, simulated annealing or basin hopping or minima hopping. You get your structure, your initial random structure, you relax it to a certain local minima, and then you need to make a move. You need to go to a new place. And so you can do random moves. So you jump your structure, you re-relax it. Hopefully it moves to a new local minima. And then you see, did the energy go down? Is the energy of this local minima lower? If that energy of the local minima is lower, then you take that result. That's good. I've made progress, bank that result. If the energy goes up, you accept it going up with a certain probability, which is determined by a Boltzmann factor, which is where the temperature comes in. Okay, so for a high temperature, you're more likely to accept a step that goes up. For a very low temperature, you won't accept any steps that go up. And so that's the basic idea behind it. So you have to design an annealing schedule by which you change the temperature over the steps. So if you're in a funnel landscape here, you can jump, and say you make the jump to the red point. If you're at a low temperature, you have a very low probability of accepting that move. Whereas if you jump to the green one, then you've got a very high probability of accepting it. And then you do the same, you'd have a low probability of accepting a jump from the green to the blue, but you'd have a fairly high probability of accepting, or 100% probability of accepting the jump of the green down to the local minima. And then when it's at the global minima, and then when it's at the global minima, it's going to be very unlikely to jump out of it because it has to jump up. Okay. So because this energy landscape is funneled, i.e. the global minima it sits on a larger scale funnel with many local minima along the path, then this is a very effective mechanism. It's basically it's very similar to if you had a ball bearing in a landscape like this and you shook it and it would sort of jiggle its way down and it would get down to the bottom and then it wouldn't likely jump out again. However, a non-funneled landscape would have, for example, this minima here being the deepest minima. Yeah? So it wouldn't have this nice structure, and so you'd have to somehow climb up here to get into the deepest minima. And in these cases, these algorithms are less good. They can get there by using these upward jumps, but they tend not to wander very far from your initial starting configuration. Okay, so that's the different approaches. Now I'm just going to take a step back and think a little bit about why is global why at first glance does structure prediction seem very difficult? And then I'm going to suggest that actually maybe it's not as difficult. It's still difficult, but maybe not as difficult as we thought it was. So the key issue here is this curse of dimensionality. It's the fact that as you get as you try to explore high dimensional parameter spaces, then the volume becomes very, very large very quickly. It becomes exponentially large with a number of dimensions. So here's just to make it concrete. If you have a single atom located in 3D, you just need 3 numbers to locate it in space. If you have 2 atoms in 3D, you got 3 numbers for each of the 2 atoms, which you can concatenate together to get 6 numbers. And so these 2 particles together live in 6 dimensions. And then these 3 particles live in 9 dimensions. Now, if you discretize space, even say you discretize it very roughly, say 10 chunks in each dimension, then the volume of the space in terms of number of points that you'd have to visit goes as 10 to the power of the dimension. So in the case of the 3 particles, you've got 1 billion points that you've got to consider. And then you add 1 more particle, and then you've got 10 to the 12 possible particle points to visit. So a truly certain global optimization algorithm has to visit, if you don't know anything about the structure of the landscape, there's no funnel, you have to visit each of those 10 to the D different points, evaluate the energy, and then choose the one that has the lowest energy. That's the only purely certain way of doing global optimization. And so you can see it quickly becomes untenable for any sort of moderately large system. So for example, a typical crystal structure with 10 atoms in the primitive unit cell, there'd be about 30 degrees of freedom. And even if it was coarsely discretized, you'd have 10 to the 30 different configurations. So if a total energy evaluation took 3 seconds, and we had a supercomputer with 1 million cores, which is possible. Okay, so it is possible to calculate energy in 3 seconds for 10 atoms. It is possible to have a 1 million core supercomputer, but it would take us 10 to the 17 years to try all those possibilities. Okay, and there are because there's 10 to the 7 seconds in a year. Now that's a lot longer, I mean, dramatically longer than the time we have in the universe. So even with this million-core supercomputer, we can't search through the grid, even a coarsely discretized grid for 10 atoms in a primitive unit cell. So we just can't do that. So we have to think a little bit differently. So there's something called the no free lunch theorem, which warns us against any sort of universally effective global optimization strategy. So what that's saying is that there's no best way of doing global optimization in general. So if someone comes to you and tries to sell you an algorithm that is the best global optimization algorithm that there is, they're wrong, because their method, they might be good for the test cases or the systems that they've tried it on, but because of this no free lunch theorem, it's kind of necessarily worse for other things that they maybe haven't tried. And so what that tells you is you have to accept the fact that there's no, you're not going to solve global optimization as a problem. And you have to adapt yourself to the particular problem that you're dealing with. So it's important to think about the actual energy landscape that we're dealing with here. When we're doing crystal structure prediction or structure prediction in general, we're not doing arbitrary global optimization. We're doing a specific global optimization of atoms on the energy landscape. And one of the features of that actual energy landscape is that atoms interact through the laws of physics, and they repulse, or they repulse, or the bonds attract through Coulomb's interaction. And in quantum mechanics, there's also the kinetic energy term as well. So it's basically, these are the two sort of main terms. There's electrostatics, and then there's quantum mechanics and the kinetic energy. And you're balancing those two different terms. So the electrostatics goes as 1 over r. It's a smooth function, okay, that goes as 1 over r. And kinetic energy in quantum mechanics, you're trying to minimize the kinetic energy, which means having smoother wave functions. So you want to smooth things out. So there's lots of things that are operating that when you move an atom around on the energy landscape, the energy doesn't jump up and down randomly or sharply. It smoothly goes up and down into different places. Now, when you put atoms on top of each other, of course, the energy goes up quite sharply. Okay, but that just means the atoms tend not to go on top of each other when they're wandering around. They wander around down in the lower parts of the valleys and so on of the energy landscape. So long as you don't put the atoms on top of each other, then things are fairly smooth. So there's a nice feature about smooth landscapes. So what I've drawn here is a one-dimensional, hand-drawn smooth landscape. And what you can see almost straight away is that there's a correlation between the size of the basin, so the width of the basin, and its depth. Because it's a smooth landscape, it means that the gradients are bounded. So you can't have very steep parts of the landscape. And so if your gradients are bounded, it means that in order to get deep, you have to travel a large distance. So the only way to get deep in a smooth landscape like this is to be in a big basin. So that's quite nice, because that's saying that the deep basins that are the ones that we want when we're doing structure prediction are actually going to be bigger basins as well. So they're going to be bigger targets. If we just try to shoot for them, we've got a relatively better chance of finding a big basin than a particular shallow basin. So there's this known correlation between the size of a basin and its depth if it's a smooth landscape. And there's more actually. So numerical experiments have been done on energy landscapes for Lennard-Jones particles, and there's a suggestion from these experiments that the energy landscapes are actually fractal in nature, and the cartoon they're fractal in nature, and they give rise to a power law distribution of basin sizes. So power law distributions and fractals are intimately related to each other. But it's worth thinking a bit about how else it might be. So it could be that an energy landscape had an average basin size with a certain standard deviation, and it was normally distributed. Okay, many things in science are in that way. There's an average, and there's a normal distribution around that average. Okay, a power law is different to that. A power law is saying that every size of basin is somehow represented. Very big ones exist, and Yeah, there's only a few very big ones, and there's loads and loads of very, very small ones, but there are still some very big ones. Whereas the normally distributed basin size would say every basin is about the same size, plus or minus the standard deviation. Yeah, there's an average basin size, and they're all of the same size. If all the basins were the same size, then effectively you have like an egg box scenario, an egg box landscape with all basins being basically the same size, and you just have to visit all of them to find out the one that is just the lowest one, okay? Because they're all about the same size. However, a power law distribution suggests a picture a bit like this on the bottom right-hand side here, and this is known as a kind of fractal called the Apollonian Gasket, and this has these fractals are made by, you make a circle, and then you pack successively smaller circles into those circles. And if you plotted the number of different basins of different circles of different sizes, you would get a power law distribution. Yeah? So there'd be a large number of teeny ones that are there, and then slightly fewer, slightly bigger ones, and so on, and then just a few very big ones. But the very big ones, by nature of being very big, are taking up quite a lot of the whole energy landscape in some way. So this is a suggestion of what the energy landscape actually looks like for smoothly interacting particles. Now, it may not be, there are still, so there may be situations where, where these big circles would never be as big as this. There wouldn't be just 3 big basins. Maybe as big as you get are these teeny ones. But still, because it's a power law distribution, it's better than being, say, normally distributed around a mean and you having to try every basin. There's a bias here that if you basically shoot darts at this energy landscape, you're more likely to hit a bigger basin. And because of this relation here, these bigger basins are more likely to be deep basins. So there's a natural bias. I proposed, and it seems to be the case, there's a natural bias of the actual energy landscape that means that the searching problem is not as difficult as it might first have seemed. So these numbers of 10 to the 23 and longer than the time of universe for 10 atoms. Yeah, you'll see very soon. I'll do searches for structures much bigger than 10 atoms, and it works quite quickly. So this is the foundations of my method, which is called Avenatio random structure searching. And as I suggested, I mean, the basic idea behind it is we imagine the energy landscape looks like something like this, and we throw darts randomly at that energy landscape, where a dart is a randomly generated crystal structure with particular unit cell shapes and volumes, and atoms randomly placed in that unit cell. And so we throw darts at the landscape, and then we do a local downhill minimization using Castep or VASP or whatever you like. You go downhill, and then you find the local minima, and then you repeat again and again and again. And if you throw enough darts, you should be able to pick up, certainly you should be able to pick up all of the fairly big basins if you throw enough darts, and also, of course, some of the small ones as well. You won't fully enumerate all of the small basins, because there still are an infinite number of basins here. If you wanted to enumerate all the basins, you still have the 10 to the 30 problem that we had before. But we just assume that those ones are likely not that important, and probably nature wouldn't be able to find them either, these tiny little basins. So that's basically the method behind Amnesty random structure searching. I published it first in 2006 and with a bit more detail in 2011. But this is basically what the code looks like. I have a Perl script, okay, very old-fashioned, but works quite well, scripting language that glues together a bunch of smaller programs. So there's build cell, which is a little Fortran program that builds random structures, and Castep relax is just a wrapper for Castep that takes a structure from build cell and relaxes it to the nearest local minima, and then you paste the results or store the results in one of those .res files that I mentioned in the previous section, and then you just do that again and again. And this is done on, that's the calculation being done on a single core, okay? But you can, the high throughput vision that I was talking about in the previous lecture means you just run thousands of these at once. So each core gets one of these little loops going in it, generating structures, and then you just sit and monitor and see what structures are generated and stored, and you can rank them by energy or other things that you're interested in. So I'm not going into a huge amount of detail here, but the basic idea is that if you're throwing darts at a target like this, your probability of success is a bit like trying to roll a dice, trying to roll a 6 on a dice, whereas the probability of rolling the 6 is the volume of the basin of your target ground state basin divided by the total volume of the whole configuration space. And say that's 1 in 50. Okay, so if you have 1 in 50 chance of hitting the basin, and notice here I've indicated that the most stable basin isn't the biggest basin. So I've said that there's a correlation between basin size and basin depth, but it's not 1-to-1. So it's not always the bigger the basin, the deeper the deeper the basin. It's just a correlation. So the deepest one might be a slightly smaller basin, or it might be even smaller still, but it will still be a relatively big basin. It won't be one of the microscopic ones that we can't see, or highly unlikely to be. Anyway, so the probability of success is the same, and the statistics of the probability of success is the same as that describes the probability of success of, say, rolling a 6 when you roll a dice. Realistically, the chances are less than 1 in 6. It might be 1 in 1,000. So it's like rolling a 1,000-sided dice and rolling 1,000. Okay, so not so likely. But one thing to realize is that with this statistics, actually, you when you're rolling these dice, it might take you 10,000 rolls to get 1,000. So the standard deviation of the number of attempts you need to roll it is equal to the mean of the probability of or 1 over the probability of the success. So if you've got a 1 in 1,000 chance, you might get it on your first roll. That's completely within the statistic, but you might have to roll it 10,000 times. So which is telling you that when it comes to judging how well structure prediction techniques are working, you can't base it on you make a tweak to your algorithm and then you run it and then it immediately found the structure. Oh, therefore you made a good tweak. No, you've got to run it multiple times to get the statistics down. So this was actually a mistake. I think a mistake that people with methods that have large numbers of parameters are bound to get trapped into, because there's a temptation to tweak those parameters, but you rarely have enough statistics to make an informed decision as to whether to tweak the parameters or not. So this is the reason why with airs, I like airs, because you don't have too many parameters to tweak. Your only thing you can really do is wait until the calculation finishes or succeeds or doesn't succeed. There's not too much temptation to fiddle with the calculations. Okay, so here's some numeric. Yes, let's put some do some numerical experiments based on this idea. So here I'm going to do some testing of this idea for random sampling of the Lennard-Jones potential. Now it's not a first principles potential, but it is a smooth and cheap to compute potential, which means we can calculate the statistics and error bars and so on. And so what I've got on the right hand side is a plot of how many times do I have to randomly generate a structure and relax it before I find the ground state HCP structure, because we know that the HCP, hexagonal close packed structure, is the ground state for the Lennard-Jones potential. So how many times do I have to randomly generate structures before I find the HCP as a function of increasing system size? And what I've got here is a linear plot. So number of atoms on this curve here, on this side, on this axis here, and number of attempts on this axis here. And you can see for up to 128 atoms, it's only getting more difficult, roughly linearly, which should be a complete shock to anyone who believes these sort of combinatorial arguments and the 10 to the 30 issues, volume of configuration space and so on. So at least for these smallish systems, it's not particularly harder whether you've got 20 atoms or 100 atoms. Okay, you just have to wait proportionally longer to find the ground state. Indeed, in the inset here, you can see as you go from 2 to 4 atoms, it actually gets slightly easier. Yeah, and then it starts to get more difficult. Well, this sort of makes sense. So as you increase your number of dimensions, you have more freedom. So I often think of it in terms of if you're in a one-dimensional world and you're confronted by a mountain, the only thing you can, and there's a deep valley on the other side of the mountain, the only thing you can do is go over the mountain. But in a 2D world, you can go around the mountain. And so actually increasing the number of dimensions can actually help things. And so actually there's an element. So I think what's going on here is that there's a competition between, increasing the dimensions is making it actually easier to find the ground state, competed with the fact that as you're increasing the number of atoms, the number of possibilities are indeed going up. And they're kind of competing against each other. And for smallish systems, small smooth systems like the Lennard-Jones potential, it largely cancels out and it doesn't get dramatically worse for larger systems. However, as you can see here, going from 128 to 256 atoms, you can see it's starting to take off. So I believe, and I think everyone believes, that in big enough systems, you indeed enter this sort of combinatorial realm where it exponentially gets more difficult. We actually need that to be the case, because if it wasn't the case, then life probably couldn't exist. We couldn't have sufficient, the universe would be really boring if it was just too easy for nature to find the ground state, because the ground state is dead and boring. Okay, so actually, we expect for big enough systems that there's still the chance for richness and complexity. But for the number of atoms that we're interested in for crystal structure prediction problems, actually, we're in a relatively good place here. So what I plotted here is a density of states of structures. So for energy above the ground state for the Lennard-Jones, I calculate how many times I find structures of different energies. And for the 128 atom example, you can see that there's a very large peak for the ground state. So it's very easily finding the ground state. It's also finding some higher energy states. And then there's quite a few that are being found at this higher energy here, which if you looked at these structures, these are amorphous or random or sort of glassy structures here. As you go up to 512 atoms, much more of the peak is in this glassy amorphous peak. Okay, but if you look carefully, there's this long tail that goes down to 0. Okay, so it's not looking, this isn't like a Gaussian here with a very small weight down at low energy. So even as you go to larger and larger systems, some weight is still finding its way down to this very low energy region. So here, look, this is comparing and contrasting a density functional theory search for 8 atoms of silicon for the diamond structure of 8 atoms of silicon versus a Tursoff potential search. Now, Tursoff potential is an old-fashioned empirical potential for silicon, and you can see the density of states looks nothing like the DFT density of structure states. So this means the energy landscape, the overall energy landscape of the Tursoff potential is just not what nature would encounter. And if you try and do random search with the Tursoff potential, it won't work. Okay, which explains actually why people didn't use random search when they were restricted to empirical potentials and were convinced that it doesn't work. Whereas you do a full DFT calculation, you have significant weight down there at the low energy. So to manage, I actually keep a track of how far I've got to go. Let's have a look. Okay, I'm going to have to accelerate a little bit because I've got some movies I want to show you. Okay, so anyway, as you go to large enough systems, eventually it gets too challenging. You hit this exponential wall, and so you need to do something to shrink the configuration space a little bit. So we have this kind of philosophy of random structure search. That if you don't know anything, use entirely random structures. But then you can actually accelerate the search, for example, by imposing chemical ideas or imposing symmetry or using experimental data. So mostly we use quite a lot of symmetry, or a little bit of symmetry in our searches to shrink down the configuration space. And we might impose chemical ideas, such as the existence of molecules or the fact that certain atoms want to be certain distances from each other. And I'll show an example of that later on. Here's a sort of what I feel is sort of advantages of random sampling. So random structure search is a very much exploration-oriented search algorithm rather than exploitation. These are words from global optimization. You have exploration, exploitation. You're balancing the two. Random sampling is kind of extreme exploration. Now, as a physicist trying to discover new things, I don't mind paying a cost penalty to doing more explanation. I'm much more, I don't mind really how much my computing bill is, so long as I can discover new things and push forward the knowledge of science. Whereas in other cases, maybe if you're more engineering or chemical environment, you might be focused on one particular chemical system, for example, the organic molecules. And then you would hone and make a very specific algorithm just for those. You'd exploit a lot of the information that you have. Other advantages of random sampling is it's intrinsically parallel. So it just works well on modern weakly coupled parallel computers. the results are uncorrelated. And that means that when you're doing this searching, if you find the same structure, the same ground state structure many times, then it's telling you something that is telling you that you're beginning to saturate the search of the energy landscape, and you're beginning to find all of the low energy structures. So conversely, if you haven't found your most stable structure more than once or more than a few times, don't stop the search. So I think it's one of the reasons why random sampling is quite robust, is that we know when not to stop searching. Yeah, if we're not finding the same structures again and again and again, we haven't finished the search. And another advantage of it, I hope you find, it's relatively straightforward to explain. I mean, I think with the explanation I've given, if you've got a bit of coding experience, you could code up a random structure searching algorithm yourself. You could use a package like ASE to do some of the tasks for you. It would be easy to do, and the parameters involved are easily communicable to other kinds of scientists that aren't computational people. So inorganic chemists, they know about bond distances and symmetries and these kind of things that we feed in. So just quickly here, I'm showing this is on the left-hand side is a snippet of an input file for boron nitride for airs. On the right-hand side are what these random structures look like. They're kind of random sensible structures. They're not completely random in the sense that they're that we let atoms go. We don't let atoms go exactly on top of each other. We have we impose a sort of random minimum separation matrix between the chemical species. This means they all look a bit chemical. They're different. I mean, you've got an example here where the boron wants to cluster together and away from the nitrogen. And then you've got an example here, which is probably quite close to the true chemistry, where you've got alternating boron and nitrogen. But we're searching all those different possibilities. We're using some symmetry as well to accelerate the search. So these are for small unit cells. Here's an example for a bigger random structure that's how many atoms has it got? 256 atoms, where we've imposed a particular minimum separation. By imposing this minimum separation, we're kind of effectively telling it a lot about the chemistry of the system. We're steering it to a sensible region of configuration space and telling it to search in this region here. And so this looks like a way that if you were interested in amorphous boron nitride, this would be a way of generating amorphous boron nitrides, or maybe other phases of boron nitride as well. Although I think cubic or hexagonal boron nitride are the key phases in this system. You can apply the same ideas to building random structures based on molecular units. Here's an example with urea, and all these random structures, they look kind of reasonable. We don't put the urea molecules on top of each other. We keep them apart from each other with this minimum separation matrix here. We're randomly choosing space groups here from this list of selection. Randomly choosing P21C. These are common space groups for these molecular crystal structures. So this is how you would do a polymorph search for urea. You can play the game of doing variable composition, as I explained with the convex hulls. So here's examples for convex hulls for carbon and hydrogen at zero pressure and at higher pressure. And you can see at higher pressure, other compositions other than methane become stable for the carbon hydrogen system. And then you can extend this to ternary searches. And here I was just showing that if you try to calculate a convex hull by taking carbon, hydrogen, and nitrogen structures from the ICSD, for whatever reason, the ICSD doesn't contain methane as a compound, and so it thinks that C19H34 is the thermodynamically stable form of carbon and hydrogen. Whereas if you do airs or random structure searching, you get a much broader coverage of all the composition space, and you certainly don't miss things like methane. Now, probably this was done in 2016, so I hope that they fixed that mistake now. But so the good thing about the random sampling is that it will give a rough idea of things pretty well. It may not be the perfect crystal structure of methane, but it gets roughly methane fairly easily. Okay, now I just want to show you a couple of movies before we finish. So here's an example of 100 doing a random. We're going to relax a random structure with 128 atoms. It's a very simplified density functional calculation. It's basically a metal. So think of it as a very metallic system. Now, for this system, I only generated one random structure ever, and I relaxed it, and I'm going to show you the results of that relaxation. Oh, hang on. Maybe, yeah, got it. So it relaxed, it looks sort of crystalline in certain regions, and then you just keep relaxing and it slaps into something that looks quite crystalline. So this is showing you the volume of this volume goes as L to the 384. The dimensionality of this problem is huge, but we're able to get to these very low energy structures because of the smoothness of the landscape. Now I've kind of tricked a bit here because, why won't it? Can I go to the next? No, maybe because it's not letting me go to the next page. There we are, back to the next page. Okay, so this is actually what we got. We didn't get the perfect crystalline ground state. We got something more interesting. We got microstructure. We got dislocations as well. So anyway, so this is just showing that you know, if crystal structure prediction was truly as difficult as these naive calculations of cursive dimensionality showed you, we wouldn't be able to get results like this with one relaxation. Here's an example for gamma boron. It's a particular high pressure phase of boron. The first thing I'll do is I'll show a random structure that relaxes to a high energy structure, and then in the next, no, it's not letting me. Let's go to the next page. Okay, so in the next page, this is a structure that's eventually going to end up at the low energy form. It forms this beautiful structure which is made up of icosahedra and dumbbells. So this was first done using evolutionary algorithms, and actually it appears to be actually easier to do with random structure searching than evolutionary algorithms. So just to finish off, a lot of what's happening now, you know, the cutting edge in this field really is to exploit machine learning methods for the energy landscape. So while old, so here's sort of a repeat of this Tursoff potential before. So while old school empirical potentials didn't really properly describe the entire energy landscape, now modern machine learning methods, this is work I did with Volker Deringer and Gabor Chani for boron, allows us to learn the whole energy landscape, which means actually we can do something like AIRS, but with faster potentials. And so this is what a lot of us are working on at the moment. And then I just want to sort of point out that there's lots to do beyond crystals, grain boundaries, point defects, surface reconstructures, and interfacial materials are all areas of active interest. And I want to finish, maybe I shouldn't do this, but I want to finish in a more negative, with a more negative slide and show things that are difficult for crystal structure. I don't want to give you the impression that it solves everything. And so there's still lots to be done. So for example, you know, there are many complex phases of boron that so far have not been found by unbiased structure prediction. The same applies for phosphorus. I'm optimistic actually that machine learning methods might get us to that level. Another challenge is to handle composition space, so ternaries or quaternaries or quinternaries. There are just so many calculations to do with all these different compositions. The nice thing about that is that it's inherently parallelizable. So if you have a big enough machine, you can just do a different composition on each of the different parts of the machine. Other challenges are these sort of complex surface reconstructions, like 7x7 reconstruction. And something that I find this would be, I'd love someone to be able to predict from first principles quasi-crystals rather than perfect crystals. And one thing to point out as well is that if you go into the ICSD structure database, the vast majority of crystal structures are actually disordered. And you'll notice I haven't mentioned how to handle disorder in these calculations. And so that's an active area that people should look at for research. And so I'll just finish off. The codes I use, CASTEP, maybe some of you are already using CASTEP. If you're not, well, you can. It's freely available for academic use around the world. It's a good full-featured DFT code that's normally very expensive if you're a company, but now we've got a license where you can use it for academic work for free. And my AIRS software, you're welcome to download and play with yourself. It's on the GPL2 license. There's some simple exercises which if you're interested, if this interested you at all, you can download, and it's on a Linux machine or something like that. You can compile it up, and there's some simple examples you can run through to see how this all works. Okay, so that's where I come to an end. I'll stop the